Hi, everyone. Thanks for coming. I'm Paul Zhang, a graduate student at MIT, and in this talk, I'd like to share some of the work we've been doing on the topology of hexahedral singularities. Our primary concern will be to convert hex meshes like the one on the left into ones like the mesh on the right. The structure of this talk will be as follows. First, we'll give a quick recap of hexahedral meshes, what they are, what they're used for, and define the interesting topological features within them, like singular curves and nodes. Then we'll discuss modifications of their topology by which singular nodes can be removed or decomposed into curves, leading to our main theoretical result that all singular nodes are at least locally decomposable. We'll demonstrate our method on a variety of meshes, thereby improving their quality, and finally conclude with some takeaways. Some of this will no doubt be familiar to you since we're at a meshing conference. In short, a hexahedral mesh or a hex mesh is a volumetric decomposition of an object into slightly deformed cubes. Here we're showing several hex meshes of various objects and cutaways so you can see on the inside they are in fact made up of squishy cubes. Hex meshes are useful primarily for spline modeling and simulation tasks like nonlinear elasticity, and they provide a decomposition of the space such that at every point there's at least locally a natural coordinate basis aligning with the hex element that point is in. In a perfectly structured hex mesh, all edges are adjacent to exactly 4 hexes and are called regular edges. More generally, unstructured hex mesh edges can be adjacent to 3, 5, or more hexes, which makes those edges singular. An important fact about singular edges is that they cannot abruptly end within a hex mesh, meaning if you have one singular edge, it must continue inside the volume, forming a singular curve. So if you look at the hex mesh on the left, since we see a valence 3 singularity on the boundary, we know it must continue on the interior, like so. When the singular curves collide with each other, they form singular nodes, depicted as the black vertices on the rightmost picture. If you were to zoom into each of these singular nodes, they would look something like this. Previous work has enumerated all singular nodes that can be formed by valence 3 and 5 singular curves colliding, and they are shown here. They are labeled with their signatures, meaning a triplet of numbers indicating how many singular curves coming out of the node are of valence 3, 4, and 5 respectively. From this list, we would eliminate the following two, since they are actually just continuations of singular curves, instead of a collision of multiple singular curves. So with that background and terminology on hex meshes established, let me pose the following question. What is a good hex mesh of a sphere? And I'm depicting here 3 views of the most common hex mesh of a sphere. I'm sure most hex meshers have seen this classic hex mesh that looks kind of like a cube inscribed inside of a sphere. So the answer is, it depends, of course, on the metric you use to quantify goodness. So let's pick a popular metric, the scale Jacobian. Roughly speaking, it measures how far away a hexahedron is from being a perfect cube. A score of 1 means it's a perfect cube, and a score of 0 means it's very distorted and not at all close to a cube. So you want a big score. Then we can compute an upper bound for the scale Jacobian of the singular elements of this hex mesh. So this mesh has 8 singular nodes, and by a symmetry argument, you can get that the upper bound of the scale Jacobian for this singular node is 0.7698. For the singular curve, though, the upper bound is 0.866. So at least according to this metric, what you can take away is that the singular nodes are a bad thing in a hex mesh. In other words, a singular node forces you to have a smaller scale Jacobian, thus higher distortion in your mesh. Can we do anything about this? Is it even possible to have a hex mesh without singular nodes? If so, does it need to be built that way, or can we somehow repair existing hex meshes that do have singular nodes so that they no longer have singular nodes? These are the questions we set out to answer. We now set our sights on the removal of singular nodes from a hex mesh. To motivate the way we do this, I want to introduce a physical intuition-based picture of singular curves. Here's a picture of 2 shoelaces pulled against each other. Since shoelaces can't pass through each other, they form a point of contact from which 4 pieces of shoelace emanate. Similarly, in 1979, Merman showed that line defect singularities in liquid crystals also cannot pass through each other arbitrarily. So now we can think of singular nodes as locations where multiple singular curves are being pulled against each other, and since they can't pass through each other, they inevitably form a contact point, i.e. the singular node. So if you wanted to untangle the two shoelaces from each other, it would be very easy. You would just pull them apart. Phrased differently, you can insert space between the shoelaces. Back to the case of hex mesh singular nodes, the analogous operation is to insert a sheet through the singular node and inflate it. This sheet passes through the space between the two singular curves and forces them to separate, thus removing the singular node. I should mention, using sheet inflation to modify singularities of a hex mesh is pretty typical. For example, when you want to convert a valence 6 singularity into a pair of valence 5s, you can just do a sheet inflation. Armed with this intuitive picture of singular nodes, let's first try to remove the singular node with signature 400. And here's a video of the process. Let's go over that a little more slowly. First, we start with the singular node. Next, we find a sheet that passes through the singular node. The red quadrilateral faces form that sheet. Next, we inflate the sheet, so the original sheet of the red quad faces is thickened into a layer of hexes marked in blue. And we're done. The sheet inflation has separated the two singular curves from each other, and there's no longer a singular node. Here's the same process on a 044 singular node. Replaying that step by step, start with a singular node, find a sheet that passes through the singular node, inflate the sheet, and no more singular node. One more example, this time there's color coding. The red edges are valence 3 singular edges, while green edges are valence 5. And the same exact process works again. First, you find a sheet, inflate it, and that's it. Now the two singular curves are separated. So far, we've shown how to decompose singular nodes into pairs of singular curves. This example is a little different. For one, the number of valence 3 and valence 5 edges coming out of it are odd, meaning in the shoelace analogy, it's unclear which pairs of singular edges come from the same singular curve. It's also not immediately clear how many singular curves are needed to form this singular node. Rather than overplaying these mysteries, let's jump to the solution. As the video shows, this node requires 2 sheet inflations to split the singular node into 3 singular curves. Some important things to note are, firstly, the initial sheet runs through a non-singular edge and inflates it into a pair of singular edges. This seemingly increases the number of singular curves. Second, after the initial sheet inflation, the only singular node remaining is of signature 222, which is a singular node we have already decomposed before. So you could interpret the 133 singular node as a combination of the 222 singular node with a valence 5 singular curve. Finally, let's speed run through the last 4 singular nodes that contain only valence 3 and 5 singular curves. The method is the same. We will repeatedly pick sheets that run through singular curves and inflate them, thereby separating the singular node into singular curves, or simpler singular nodes. After enough iterations, we end up with just singular curves. People who pause and rewatch these decompositions might notice singular edges colored blue. Blue encodes singular edges of valence 6 or higher. So in the process of decomposing singular nodes with only valence 5 or less, we hit intermediate states containing valence 6 singularities. Ultimately, though, since valence 6 curves can be split into pairs of valence 5 curves, the final meshes only contain singularities of valence 5 or less. So with this enumeration, we've shown that the most common singular nodes in hex meshing can all be decomposed into singular curves. But there are an infinite number of singular nodes possible. So what about nodes with valence 6 or higher? This brings us to our main theoretical result, which is that it is possible to decompose any singular node regardless of valence into curves with just sheet inflations. This is stated more precisely in the paper. I won't go into details of the proof here, but for some intuition, the proof is actually a statement about triangulations of a sphere. By intersecting a sphere around a singular node, you can map any singular node into a sphere triangulation. This turns out to be a very handy way to think about singular nodes. The remaining step is to find cycles in the sphere triangulation that split the sphere into two disk triangulations with a total vertex bound on each disk. Cycles in a sphere triangulation correspond to partial sheets local to the singular node whose inflation breaks up that singular node into two slightly simpler singular nodes. The proof essentially establishes that such a cycle always exists. Now let's extend our result from individual singular nodes to full hex meshes. The core of our algorithm is iterative sheet inflation. The hard part is building the sheet that needs inflating. Using the sphere hex mesh as an example, we randomly select an initial singular node marked in blue. Next, we select a local set of quad faces that cut through that node. Then we propagate the local set of quad faces outwards in a greedy fashion until it collides with the boundary or with other singular curves. Now we detect any singular nodes on the boundary of the partially constructed sheet. These are marked in yellow. We randomly select one as the next node to focus on. We need to tell the partially constructed sheet how to pass through that selected node. This is done using a graph shortest path algorithm on the sphere triangulation of that node. Details in the paper. Continue extending the sheet. And finally, the sheet is completed. Inflate the sheet. And notice that with this one sheet inflation, we've managed to remove 3 singular nodes simultaneously. Here's the rest of the sphere decomposition. Here's some examples of our algorithm performed on hex meshes with different singular graphs. In each case, we managed to remove all singular nodes of the mesh with a series of sheet inflations. There's one more example of a hex mesh of a cactus that has all its singular nodes removed. Admittedly, the geometric fairing step of our codebase hiccuped on this example, so you'll see some tangling at the top of the cactus on the right, but those are purely geometric artifacts. The mesh is still an all hex mesh with no singular nodes. Here are some numerics where we show for various meshes the best scaled Jacobian score for the mesh we can obtain before and after singular node removal. In particular, I'll direct your attention to the 400 singular node. The original max scale Jacobian is 0.769, exactly the theoretical upper bound achievable with a singular node. After the node is removed, the scaled Jacobian jumps almost exactly to the next theoretical upper bound achievable of 0.866. The same phenomenon can be seen in the sphere mesh, though the scaled Jacobian greatly increases. This is due to the removal of all 8 400 singular nodes. Lastly, I'll point your attention to the 0012 singular node. Again, by the symmetry arguments, we know that any mesh with this singular node present has a scaled Jacobian upper bound of 0.761. Removing that singular node brings up the score to 0.926 and a new theoretic upper bound of 0.951. The valence 5 singular curves are slightly less mesh distorting than valence 3 curves. To summarize, these are the 2 points I've repeated throughout the talk. Singular nodes distort the mesh, and singular nodes are removable with sheet inflation. Now let me add a takeaway from far left field. Well, it's more of a question than a takeaway. For people that watch this who study frame field computation, I know the most popular, if not the only frame field energy people optimize is Dirichlet energy. But Dirichlet energy likes to decrease the number of singularities, which as intuited by the shoelace analogy, will force singular curves to collide and make singular nodes. So is Dirichlet energy really the right thing to optimize for? To close, I want to thank the Summer Geometry Initiative that let me lead a team of SGI fellows to work on this project. I'm happy to take questions.